Dear students, welcome to another lecture in statistical quality control. We were seeing about control charts. Till now we have seen control charts for variables. Today let us discuss about the control charts for attributes. Now before proceeding to the control charts of attributes, let us see some definitions like defect and defective and fraction defective. Okay, let us see first what is a defect and what is a defective. You see, an item is said to be defective if it fails to conform to the specifications in any of the quality characteristic. Suppose there is a shaft, it should have certain diameter and it should have certain length. These are now two quality characteristics. If it fails in any of these things, if the diameter is okay, the length is not okay, it fails. Or if the length is okay, diameter is not okay, then it fails. You see, then that part itself becomes a defective part, like that. So each characteristic that does not meet with the specifications is called as defect. You see, in our case, where now we have a shaft, there are two quality characteristics like diameter and the length. If only diameter, it is not conforming, but the length is conforming, that means there is one defect, and because of that one defect there is a one defective piece. Suppose it is not conforming to the length as well as the diameter, then it has two defects but one defective part, like that. So an item is said to be defective if it contains even one defect. Even one defect if it is having, then we can call that that item or that article or that workpiece, you can say, or that finished object as a defective object. Okay, for example, if a casting contains undesirable hard spots, blowholes, cracks, etc., the casting is said to be defective, and these hard spots, blowholes, cracks, etc., these are called defects. Okay, so that is the thing. Say in one defective part there can be many defects. Okay, so you differentiate between defect and defective. Okay, now next let us talk about fraction defective. Now fraction defective, when we say, what are we meaning? It is the ratio of number of defective articles to the total number of articles actually inspected. For a simple example, suppose we are inspecting 10 articles. Out of 10 articles, 3 are defective. Now the ratio of defective articles upon total total inspected articles, that means 3 upon 10. This is the fraction defective. 3 upon 10 is 0.3. Now 0.3 is the fraction defective, and it is always expressed as decimal fraction. Okay. Now let us come to the control charts for the attributes. You see, for variables we have seen the control charts, and those are X bar chart and R chart. Now we are going to see control charts for attributes, and the first such chart is P chart. P chart is an attribute control chart because it is drawn for attributes. Okay, it means that it is used for those quality characteristics which can be classified as either conforming or non-conforming to the specifications, whether it is passing the quality check or it is failing the quality check. It is so simple. It is not like in variables. See, the diameter means you have to measure and see if it is 50 point 02 or 50.01 or 50.001 or what diameter it is. There are a number of possible results. Here no, it is only two results, either pass or fail, either accepted, not accepted, or either it is conforming or not conforming. That's all. Okay, see, all attributes. And also, as we have seen before, these are all whole numbers, they won't contain fractions. Okay, when we are talking about attributes. Okay, in other words, items conforming to the specifications. If it is conforming to the specifications, specification means design specifications. If it is conforming, that means it is according to the need, as per the requirement. If it is as per the specifications, it is, then it is called non-defective. But the items non-conforming to the specifications are defectives. Okay, therefore P chart is called as a defective chart, or chart prepared for defective parts. It's like that. Okay, for example, dimensions of male and female components such as shaft and its mating hole are checked by go and no go gauges. So when go and no go gauges, if you are checking, see, either it is accepted or it is rejected. It's simple like that. See, such kind of attributes. For that we are drawing the P chart. Okay, in case of P chart, we calculate fraction defective P for each subgroup or sample, and then we plot these calculated fraction defectives against the corresponding subgroup number or sample number. Therefore, P chart is also known as fraction defective chart. Either you call it as defective chart or fraction defective chart. Okay. Now, let us see how to draw this P chart. The first point is you have to record the data. That means know whether the for each subgroup, number of articles inspected and number of defectives. This you have to you have to record the data, how many are inspected, and out of that how many are defective. And second point is you have to calculate the fraction defective P for each subgroup. Suppose see, when you say subgroup, no, in each subgroup there will be certain items. Okay, and like that many subgroups can be there. Okay, so now what we are doing is for each subgroup we have to calculate P. P is fraction defective. Now how do you calculate? See, it is simple. Number of defective parts upon number of the inspected parts. Okay, like I said, if 10 are there, 10 you have checked, out of that 3 are found to be defective. That means 3 upon 10. That is P. Like that you calculate. Okay, now the third step. Now you have to calculate the average fraction defective. That means P bar. See, in the second step what we are calculating is only P. In the third step what we are calculating is P bar. Because for a chart, how many P's you will be calculating? As many as the samples are. How many P bars you will be calculating? Only one. Okay, you understand? This is we are going to calculate only one P bar. But how many P's? How many ever subgroups are there? So many P's we will be calculating. Okay, now what is the formula for P bar? P bar is the total number of defectives in all the subgroups. That will be the numerator. And then the denominator, total number of articles inspected in all subgroups. Okay, like that you calculate P bar. Now next step is to the next step is you have to compute the control limits. Control limit means upper control limit and lower control limit. Now for this P chart, what upper control limit, lower control limit, we are using the formula are given here. Now see at this level how we are arriving at these formulae, what are the mathematics behind it, that we are not dealing. You see, at your level you need not worry about from where these things have come, only that we are using this formula because we don't have so much of time, and and our subject doesn't deal with so much of mathematics to to be deriving these formulae and investigating. Okay, so we just use the formula. Okay, now the upper control limit p bar is p bar plus 3 square root of p bar into 1 minus p bar upon n, and the lower control limit is the same, only here instead of plus we are using minus. So these are the control limits. You will find out these two values. Okay, once you find these, these are the upper control, lower control limit, and this is the center line p bar. So and you will be getting number of p's depending upon the how many subgroups are there. So every time you get p, you will be marking 1 point. On the x-axis you will have the number of the subgroups, that means first group, second group, third group, like that. And whatever p is coming, you have to put it on the y-axis, and you will be getting points. Okay, like that you have to draw the control chart. Okay, now whatever on the control chart, plot the control limit as calculated and each point as obtained. The points falling outside the control limits are then identified. If something is falling outside, that shows there we are not having control over the process. Okay, next, if the points fall outside the control limits, there may be two reasons. Assignable causes of variation may be present, or the standard quality level is different for assumed standard fraction defect. So here the assumed standard standard defective can be changed to bring it into within the control limits. But anyway, that you have to see how stringent quality measures you want to adopt. Okay, anyway, this is how you draw the p chart. Okay, next, now what are the objectives of p chart? Why do we draw the p chart? See, because of p chart, you remember one thing, drawing variable control charts like x bar chart and r chart, these are for that we use precision control or precision measuring instruments, and it takes time and more accuracy and other things. So more time is required and more money is spent there. Whereas in case of the attributes, the cost involved and the time involved are less. So because of lower inspection and maintenance costs of p chart, they usually have a greater area of economical applications than control charts used for variables. Okay, now the objectives are, that means what? More often people use this, because this gives a rough idea. But if you want more accurate accurate quality charts, then you go for x bar chart or r chart. But this can be quickly done. So when large quantities are involved, when less money is to be spent, they go for p charts. Okay, attribute charts, not only p chart, the other things also. Okay, to find out average proportion of defective articles submitted for inspection over a period of time. Over a period of time, see, suppose over a period of 1 week or 1 month or like that, or a period of time, if you want to say what is the average proportion of defects, that means out of you can say out of every 100 pieces 2 pieces are defective, that way you can conclude. See, to find out such kind of proportions, you use P chart. And in a sampling inspection of large lots, when large lots are there, number is too much, you cannot do the X bar R charts, because you cannot be attending to so many parts and when the time available is less. So then you go for attribute charts like P chart. Okay, to bring attention to management about any changes in average quality level. So if something is not up to the mark, you have to bring to the notice of the management, top management, or whoever is responsible to take action. To those people we have to bring to their notice. Then to identify and eliminate causes of bad quality. Now all these control charts we are doing for that only, to identify the causes and to eliminate them, and to provide useful record of quality history management, and finally to suggest whether it is necessary to use X bar R charts to diagnose quality problems. See, even this also it does. It will suggest you whether X bar chart or R charts are necessary or not. That also P chart provides. Okay. Now that is about the P chart. Now the next attribute chart. This is NP chart. Totally we are going to see 4 types of attribute charts. First one we have seen P chart. Second one we are seeing now, that is NP chart. And the third one we'll see C chart, and the fourth one we'll see U chart. Okay, these are the 4 charts for attributes and 2 charts for variables. 2 charts are X bar chart and R chart. Okay, now NP chart. N normally when you're writing, this N is written small and P is written as capital. So NP chart. See, NP chart is also an attribute chart, and it is almost the same as P chart. It is almost the same. A little difference, and we will see what it is. Okay. When number of articles in subgroup is same, then use NP chart. Then use of NP chart is preferred than P chart. Sorry. Now what are we saying? See, if you are having 10 samples, and in each sample how many articles are there? Suppose in each chart equal number are there. In each chart, each sample 5 articles are there. That means in the first 5, second 5, third 5, fourth 5, fifth 5, and up to 10th 5. If everything is same, then NP chart is preferred. But suppose that sample size is different, that means the number of articles in subgroup is different. That means in the first 5 samples you have taken, in the second sample in the first 5 articles you have taken, in the second sample you have taken 6, and then third you have taken 4. That this is varying like that. So in that case you use P chart. Okay. In the NP chart, we plot number of defectives found in each sample. Therefore, you see here now, what are we plotting? We are plotting the number of defectives, not a fraction of defective, fraction defective. You see there in P chart it is fraction defective. Here what are we plotting? Number of defectives. Okay, therefore NP chart is known as also known as defective chart. but the NP chart was called as fraction defective chart. This is called as, okay, this is called as defective chart. Okay, in NP chart there is no need to calculate the fraction defective. See, that means no, here in P calculation, no, this second point is unnecessary. This second point is unnecessary. You need not do in case of NP chart. Okay, so in NP chart there is no need to calculate fraction defective for each subgroup. What is which is necessary step for P chart? In short, NP chart is used to express results in whole numbers instead of fractions. So P is using fractions, fraction defectives, whereas NP is using whole numbers. That means, you know, in 10 pieces, in a sample of 10 pieces, 3 are defective. So there we calculated fraction defective and we used 0.3. Here, no, directly you use 3. There is no further calculation is necessary. 3 upon 10 is equal to 0.3. This step is unnecessary in case of NP chart. Okay, now let us see how to draw the NP chart. First, you record the data. Record the data means, you know, in each subgroup, number of articles inspected, number of defectives found. Okay, these things you get. And then, now, directly calculate the average fraction defective P bar. Now P bar is total number of defectives in all subgroups upon total number of articles inspected in all subgroups. That is sigma NP upon sigma N. Okay, now you have to find out the calculate the central line. Now for central line, what are we doing is you multiply the calculated value of average fraction defective P bar by N. Okay, and we get the value of NP bar. Now this NP bar is used as the center line for NP chart. Okay, so thus the center line for NP chart is NP bar. Okay, now calculate the control limits. You know, this is these are the formulae. That is, upper control limit is NP plus 3 square root of NP bar into 1 minus P bar. Okay, and lower control limit also is the same, only that plus is replaced by minus, and you plot the chart. This is the way you draw the NP chart. Now let us differentiate between these two, P chart and NP chart. What is the difference? Now the basic principle is, in P chart, no, fraction defective for each subgroup is used, whereas in NP chart the whole number of defective, that is the number of defectives found in each sample is used, and it is plotted against the corresponding subgroup number. Okay, the second one, calculation of fraction defective for each subgroup. In P chart, this step 2 is necessary, whereas in NP chart it is not needed. It is not necessary. Not needed means we don't know it. Okay. Third one is alternative name. Alternative name for P chart is fraction defective chart, and NP chart it is defective chart. And way of expressing results after analysis. Results are expressed in fraction in case of P chart, and in NP chart results are expressed in whole numbers. A center line in case of P chart is P bar, and in case of NP chart it is NP bar. And where we use is, you see, when all the subgroups have same number of samples, then we use NP chart. And if it is different, each sample has different number of items, then we use P chart. So these are the differences. Now let us see now see the NP chart is better over P chart. It has advantages. What are the advantages? Let us see. NP chart saves one calculation for each subgroup. See, if there are 10 subgroups, 10 calculations are avoided. Okay, that is division of number of defectives in a subgroup by subgroup size to calculate fraction defective is not necessary. You see, a little less calculations are needed in NP chart. And second is to understand also, NP chart understanding is easier because we are using whole numbers. Directly we are saying, okay, we checked 10, 3 are defective. We are using 3 in the chart. So simple. Now in case of P chart, no, you have to say how this fraction is coming. Okay, so people find it difficult to understand. Okay, so these are the P chart and NP chart. Now let us see the third one, that is the C chart. Now C chart also is used for attributes only. Okay, it is like a P chart only. Another control chart we are using, that is C chart, and this is for attributes. C chart shows the number of defects. You see, here it is not defective. Here using the thing defects. Okay, we are using defects or non-conformities in an inspected unit, such as automobile. You see, where in C chart normally where it is used, where in one a big piece many small defects can be there, like in an automobile casing. An automobile, suppose engine block is there, automobile engine block, or chassis, or some such thing, or cloth also. You see, when cloth is manufactured, you see, it is manufactured in a long what we should say, as a long strip, and it is wound, and I think it is called it is wound into some thorn or something they call it. Okay, but in the cloth also there can be number of defects. Oh, here some defect is there, some here one pinhole is there some the thread is not straight, and some lump is formed or something like that. It can happen in the cloth. Okay, so in such cases, you find out, you use C chart. You see, and this is based on Poisson's distribution. Okay, now see, you need not worry what is Poisson's distribution and all. Just remember that it is Poisson's distribution. Actually, you studied in mathematics, only that you have to recollect your those mathematical lessons. Okay, now C chart is applicable if all samples or subgroups have the same number of articles. That means C chart is applicable to subgroups of same size. You see, like when we were using P chart and NP chart, P chart was using for varying sample sizes, whereas NP chart was using for same sample size. So C chart is used for same sample size. Okay, that means equal number when it has. That means first sample has same number, suppose 6 items. Second sample also has 6 items. Third also has 6 items. Like that, if you have 10 samples, all the 10 samples are having 6 items. At that, if it is like that, you use C chart. Okay, and if it is not like that, and each sample the number is varying, changing, then you use next chart, that is called U chart. Okay. So let us see further. Now how to draw C chart. First you have to record the data. That is the first step for all the things. Second is because it is used for same sample size of the samples. You see, one step is omitted. Okay, you need not calculate that second step that we used in the P chart. Okay, now directly we will find out what is C bar. C bar. C bar is the central line. Okay, that is the number of defects in all subgroups upon total number of subgroups. See, here we are using defects. Defect means, in one piece there can be number of defects. Okay, you remember, defects, no, many number can be there in one object or in one work piece. Okay, so C chart and U chart are used for defects, and P chart and NP chart are used for defectives. Okay, so once you calculate the central line C bar, then you calculate the upper control limit, lower control limit using this formula. That is, upper control limit is C bar plus 3 square root C bar, and the lower control limit is C bar minus 3 square root of C bar. Okay, now plot the chart, and you have to plot each point as obtained, and the control limits we have calculated, and use those control limits. You have found out the center line also, you use that. Okay, and the points which are falling out outside the control limits are to be identified, and you have to analyze later why such thing has happened. Okay, now applications of C chart, where you use the number of surface defects in an aircraft wing. If an aeroplane is there, it is traveling, so there, you can say, you can choose 1 square meter area, and in that square meter area you can see how many defects are there. Okay, you cannot say the entire thing is defective and you cannot throw. See, you have to say how many surface defects are there. You have to find out. Okay, number of defects such as blowholes, cracks, etc. in a casting. In case of casting also you can use C chart, and in case of cloth also, per unit area, that means 1 square meter area, how many defects are there in the cloth, and if too many are there, they will simply, normally some of the companies are so quality conscious, even a small defect if they find out, they will cut that portion and throw it. They will sell it for seconds or something like that. Okay, then number of surface defects in a galvanized sheet. Suppose you have made the sheet to be galvanized, but here and there the substrate material is exposed. See, that means there the protection is lost. So how many such places are there, how many defects are there? For finding out that, you can use C chart. And number of small holes in glass bottles. If glass bottles are being manufactured, there in the glasses bubbles may come, like small holes, small bubbles, you can say. So bubbles are not desirable. If anything is there, to bring control into the process, you may use C chart there. Okay, now next let us talk about U chart. Now U chart is similar to C chart, and like C chart, U chart also shows the number of defects, not defective. So this also is used for defects, like automobile casing and cloth, etc. And therefore U chart is also an attribute chart. And like C chart, U chart is also based on Poisson's distribution. The only difference is if the sample size is uniform. If the sample size is uniform, we use C chart. If the sample size is varying, then we use U chart. That's all. Now let us see how to draw. Now here one step more will be there, because the sample size is different. Okay, first record the data, second calculate the sample size n. N is total number of articles inspected in all samples divided by the total number of samples. This is the formula. Then next calculate the center line, that is u bar. For a u bar, it is total number of defects found upon total number of items inspected. And then you calculate the upper control limit, lower control limit using this formula, here. And then and you have to find out, you have to calculate the value of u for each sample. You have to calculate for each sample. That is, u1 is equal to total number of defects in first sample upon total number of articles inspected in first sample. Like that, you have to find out u2, you have to find out u3, you have to find u4, u5. Like that, if 10 samples are there, you have to find out for 10. If 20 are there, you have to find out for 20. Okay, like that. Then you have to plot the chart. Now that means what? U chart plotting is little difficult or time consuming compared to the C chart. Similarly, plotting of P chart is difficult than NP chart. Okay. So you plotted the chart, and now let us see the summary of attributes. Summary of attribute charts. Now the summary is, say, P chart is used. It is a control chart for fraction defectives, whereas NP chart is number of defectives. And there is something called as 100p chart also. This is the chart for percent defectives, that we have not studied. Anyway, another thing is C chart. C chart is the control chart for number of defects per item or per part. And when the sample size is uniform. And U chart, you can add one more. U chart is control chart for number of defects per item when the sample size is varying. Here also you can write that. In P chart, no sample size is varying. In NP chart, it is uniform. Okay, like that. Now let us see this much, and then we'll stop. Difference between variable control chart and attribute control chart. Now variable control chart examples are X bar chart and R chart, whereas attribute control charts, P chart, NP chart, C chart, U chart, these are attribute charts. Now data required. Now data required is a measured quantity which is used by measuring instruments, precision measuring instruments like screw gauge, vernier caliper, or like that, or dial gauge indicator or surface roughness meter, something like that. With that you calculate, okay, for X bar R charts. Whereas for attribute charts, data required is attribute data. It is simply, is it confirming or is it not confirming? Is it passing or is it failing? It's like, simple gauges like go gauge, no go gauge are used. Okay. And external control of individual quality characteristic. What are we controlling? Controlling of individual characteristic. Whereas in attribute charts, control of proportion of defectives or defects. That's what we are controlling. Then information obtained. Yes, provide detailed information on process average and variation of control of individual dimensions. It gives more detailed information, whereas attribute charts won't give so much. They do not provide detailed information for control of individual dimensions. Only it will say it is accepted or not accepted. Why it is not accepted, what was the problem, these attribute charts will not be able to tell. For that you have to go to variable charts. Okay. Now need of special training. Yeah, special training is needed when you are using precision instruments. So variable charts, you need special training for the people who are working in the quality control department. Whereas for attribute charts, no big training is required. And the time required is for variable charts, it is a time consuming process, whereas in attributes control charts, less time is required. Okay, for the sample size, variable charts, smaller sample size will be smaller, because that itself they cannot be calculated, it is taking so much time. Whereas in attribute charts, the sample size big, large, generally large. Okay, then cost involved also, if you talk about cost, more cost, more cost is there, high cost, because high cost is high because data is collected by using measuring instruments which are subjected to early wear and tear. Also they need to periodically recalibrated, they need to be recalibrated. So therefore variable control charts are costly, more man hours are required, you see, more precision instruments are required, and they need to be periodically calibrated, and normally they get wear off, wear and tear is coming, because of that cost is involved is more. Whereas in attribute control charts, the cost is comparatively less, because it is most often by simple gauges like go gauge, no go gauge. Okay friends, then today we will stop here. We have seen the control charts used for attributes, and also we have seen the comparison between control charts for variables and control charts for attributes. Okay, we will continue in the next lecture. Thank you.